Eutectic system. At the end of this lecture, you will be able to define what is eutectic reaction, interpret the various regions and boundaries in a eutectic phase diagram, differentiate between a hypo-eutectic alloy and hyper-eutectic alloy, explain the microstructure evolution of eutectic alloy and hypo and hyper-eutectic alloys. What is an eutectic reaction? When a liquid transforms simultaneously into two solid phases on cooling, such a reaction is called eutectic reaction. Liquid on cooling forms two solid phases, alpha and beta. So in this diagram you can see there is a alpha phase, there is a beta phase, and there is a liquid phase. As is evident from 1-to-1 rule, the alpha phase and liquid phase should have a two-phase region in between, alpha plus L. Similarly, there should be a two-phase region, beta plus L, here. So as can be seen, this diagram is actually a portion of the eutectic phase diagram. So to understand better, let us discuss about the eutectic phase diagram in detail. There are three single phase regions: the alpha region, the liquid region, and the beta region. And this entire phase diagram is that of a lead-tin alloy. Pure lead is 0 weight percent tin, and as the weight percentage of tin is increased along x-axis, you can form from pure lead, you can go to pure tin, 100% tin. It is a binary alloy, but there are two solid phases. What does this mean? Here is where the concept of solid solutions with limited solubility arises. The alpha phase of solid or lead-tin alloy is one in which lead is the solvent and tin is the solute. That is, it is rich in lead, whereas beta phase is rich in tin. Lead is the solute in this case. The solubility limit of tin and lead is nearly 19%, whereas the solubility limit of lead and tin is very near to 2.2%. So, only solids with limited solid solubility exhibit an eutectic phase diagram. The various regions are alpha, liquid, beta, the single phase regions, and as I told earlier, by 1-to-1 rule, we have alpha plus liquid region in between alpha and liquid, beta plus liquid region in between beta and liquid, and alpha plus beta region between alpha and beta. So there are 3 single phase regions and 3 two phase regions. What about the boundaries separating the different regions. The curves separating the liquid region from the two-phase regions are known as liquidus curves. The curves separating the solid region from the two-phase region, which is a combination of solid and liquid phase, are called solidus curves. The curves separating the single phase solid region from the combination of two solid phases region are known as solvus. And there is another distinct type of a horizontal line separating the three two-phase regions, that is alpha plus L and beta plus L is separated from alpha plus beta by this horizontal line, which is called as eutectic horizontal. So, eutectic horizontal corresponds to a temperature of 183 degrees Celsius, which is called as the eutectic temperature. The composition 61.9 weight percent of tin is called as eutectic composition. Why? Because as you can see, whatever at all other compositions, say 30 weight percent tin, it is completely liquid at say 300 degrees Celsius. When it touches the two-phase region, or when it touches the liquidus curve, it starts to nucleate, and the nuclei grows as the temperature further falls, and it is a complete solid once the eutectic horizontal is reached. That is, freezing occurs over a range of temperatures for all other solids. If you take say 10 weight percent also, the freezing occurs over a range of temperatures. But in case of the eutectic alloy, it is directly transformed from the liquid phase to alpha plus beta phase at a single temperature, just like pure elements. So, such an alloy which exhibits a single freezing point is called as eutectic alloy, and the corresponding temperature of freezing is called the eutectic temperature. And the point on the phase diagram comprising of CE and TE, eutectic composition and eutectic temperature, is called as eutectic point. The horizontal line in the phase diagram passing through the eutectic point is called as the eutectic line or eutectic horizontal. Since the temperature remains invariant along the horizontal line in a phase diagram, the reaction is said to be an invariant reaction, and it is an isothermal process. Transformation from liquid phase to simultaneously into two solid phases is an invariant reaction at this eutectic point. So we will recapitulate whatever we have seen. Three single phase regions are found on the diagram: the alpha phase, the beta phase and the liquid phase. The alpha phase is a solid solution rich in lead. tin is the solute, whereas lead acts as solvent in the alpha phase, whereas in beta phase, lead is the solute. Lead is the solute. It is rich in tin. The solubility in each of these solid phases is limited. So these are solids with limited solid solubility. The solubility limit for the phase corresponds to the boundary line between alpha and alpha plus beta, that is the Solvus curve, and alpha and alpha plus L, that is the Solidus curve. So the Solidus curve and the Solvus curve together sets the solubility limit. Okay. So here in this diagram you are having all the different regions and boundaries marked out. You are having 3 single phase regions, L, alpha and beta, 3 two-phase regions, L plus alpha, L plus beta and alpha plus beta. So there are liquidus boundaries separating the liquid region from the two-phase regions. There are solidus boundaries separating the solid regions from the two-phase regions, and there are solvus boundaries separating the alpha from alpha plus beta and beta from alpha plus beta regions. So it is explained clearly in this slides. So a further discussion of limited solid solubility. The alpha is a solid solution of tin in lead, that is tin is the solvent, lead is the solute. It is rich in lead. The solubility of tin in the solid solution is limited. At 0 degrees Celsius, only 2% tin can dissolve in alpha. As the temperature increases, more tin can dissolve in lead, and at 183 degrees Celsius, 19% of tin can dissolve in lead. This is the maximum solubility of tin in lead. That is 19% of tin in lead is the maximum or limit of solid solubility of tin in lead. So now this is a digression on solids with limited solubility and their microstructure evolution. This portion is especially for your understanding of microstructures. Okay. Suppose you consider a 2% tin alloy, that is 2% of tin in lead alloy. At about 323 degrees Celsius, the alloy is completely in liquid state. On reaching around 320 degrees Celsius, there is nucleation, and on further cooling below 300 degrees Celsius, there is a polycrystalline alpha phase. There is no alpha plus beta phase, so it is completely in alpha phase. This is a single phase solid solution. Whereas now let us consider a 10% tin in lead alloy. When you consider a 10% tin lead alloy, it touches the, note the difference. For a 2% tin in lead alloy, the liquidus and solidus curves are almost coinciding, whereas for a 10% tin in lead alloy, the liquidus and solidus curve are not coinciding. There is formation of alpha phase through nucleation just as earlier, and a polycrystalline alpha phase is formed here. But here you can look at the phase diagram. For a 2-8%, the entire stretch of cooling from 300 up to say 0 degrees centigrade occurs completely in alpha phase, whereas for a 10 weight percent tin and lead alloy, when cooled below say 150 degrees Celsius, the alloy has to enter the alpha plus beta region. So there is dispersion of beta phase in the alpha phase once it is cooled below a particular temperature in the solver's curve. So such a mechanism in which one solid phase is dispersed in another solid phase is called as dispersion strengthening, and you will come across the same concept when you are dealing with the mechanical properties of materials. So this is a digression from this topic, but the concepts discussed here will be of use when we are dealing with unit number 3, the mechanical properties of materials. So now we will discuss about an eutectic alloy in detail. The alloy containing 61.9% tin, which is called as eutectic composition CE, is called as an eutectic alloy. The word eutectic means easily melting. It is derived from the Greek word eutectos, which means easily melting. Why easily melting? As you know from the phase diagram, the melting point of lead is 327 degrees Celsius, while that of tin is 232 degrees Celsius. Whereas for the eutectic alloy, it is 61.9 weight percent tin and lead alloy, the melting point is 183 degrees Celsius. So it is evident that this alloy has a much lower melting point than both the constituent elements. It is easily melted, and hence the name eutectic alloy. Solidification of this alloy occurs at a single temperature, as we have seen in the phase diagram. It occurs at a single temperature 183 degrees Celsius, which is called as eutectic temperature. Above the eutectic temperature 183 degrees Celsius, the alloy is all liquid, and below the 183 degrees Celsius, it completely transforms into two solid phases, alpha plus beta. The composition of the two solid solutions are given by the ends of the eutectic line. So here recall about the tie line rule. The tie line constructed at a particular temperature will give you the compositions of the phases involved. So here the alpha phase has a composition of C alpha is 19 weight percent tin, whereas C beta is 97.8% tin. Note the stark difference. The alpha phase has just 19 weight percent tin, whereas the beta phase has 97.8% tin. So in the thermodynamics of the eutectic reaction, there is not only removal of latent heat, but also redistribution of the two different kinds of atom specimens. This occurs by diffusion. And also note that alloys solidify over a range of temperature called as freezing range, whereas in case of eutectic alloy, the transformation occurs at a particular constant temperature called eutectic temperature. So here the microstructure evolution of an eutectic alloy is illustrated. Just above 183 degrees Celsius, there is formation of nuclei. The nucleation and growth leads to a polycrystalline eutectic microconstituent. Why do I call this as an eutectic microconstituent? It is a characteristic of an eutectic alloy. When an eutectic alloy is cooled below the eutectic temperature, the simultaneous formation of alpha and beta phase is such that it forms a lamella, that is thin sheets or plates of alternate alpha and beta regions. The yellow phases are alpha while the red regions denote beta. So there are alternate strips or lamella or plates or sheets of alpha and beta in the eutectic microconstituent, and note that it is a polycrystalline structure because of various nucleation sites. So, as the atoms are redistributed during eutectic solidification, a characteristic microstructure develops. In the lead-tin system, the solid alpha and beta phases grow from the liquid in a lamellar or plate-like arrangement. The product of the eutectic reaction has a characteristic arrangement of the two solid phases, and this characteristic arrangement is what is called as eutectic microconstituent. The eutectic microconstituent is 100% of the liquid is transformed into, that is, the liquid is fully transformed into eutectic microconstituent. So now, what is hypoeutectic alloy? An alloy with a composition between 19 and 61.9 weight percent tin is called a hypoeutectic alloy. So let us consider a 30 weight percent tin in lead alloy that is being cooled. As illustrated in this diagram, when the 30 weight percent tin alloy is cooled from the liquid phase, on reaching the liquidus curve, there is nucleation, and on further cooling below the liquidus, there is growth of the nuclei, and on reaching the eutectic horizontal, there is formation of eutectic mixture over the proeutectic alpha that has been formed. So, the resulting microstructure when cooled well below the eutectic temperature is called a combination of proeutectic alpha and the eutectic mixture. Eutectic mixture is the lamella of alternating plates of alpha and beta. So, this clearly illustrates the microstructure evolution of a hypoeutectic alloy. When the alloy is cooled below 183 degrees Celsius, all of the remaining liquid goes through the eutectic reaction and transforms to a lamellar mixture of alpha and beta. The microconstituents are proeutectic alpha and a lamellar mixture of alpha and beta as shown in this figure. Similarly, a hypoeutectic alloy is an alloy with a composition between 61.9% and 97.5% tin. Similar to a hypoeutectic alloy, in a hypereutectic alloy, the microconstituents will be proeutectic beta and a lamellar mixture of alpha and beta. So, with this we are completing the discussion on a eutectic system. As I promised at the beginning of the lecture, I hope you can answer the questions. Define a eutectic reaction. Draw and mark the various regions in a eutectic phase diagram. Differentiate between hypoeutectic alloy and hypereutectic alloy. Explain the microstructure evolution of an eutectic alloy, a hypoeutectic alloy and a hypereutectic alloy. In addition, you must also be familiar with various terms involved in the discussion, such as limited solid solubility, eutectic composition, eutectic temperature, eutectic horizontal, eutectic mixture, and dispersion strengthening. Hope the lecture was useful to you. We will continue with the possible question that can be asked in the examination and how to answer for that question. Okay. So here I discuss about the ways of answering the questions that have come in the previous university exam question papers. We were discussing eutectic systems. This is one possible question. Draw a typical equilibrium diagram for a eutectic type of system with limited solid solubility and explain its important features. The other possible question is explain in detail the different phases in eutectic phase diagram with the microstructural changes during cooling. So you can see the two possibilities are regarding the eutectic system, but a student should answer with reference to the context, because the evaluator or the examiner will be given a key based on which he will evaluate the student's answer. So it is quite important on how you present your answer, because depending on your presentation, your marks may vary. Here I have developed a holistic rubric based on which these questions will be evaluated. First, let me deal with this question. Draw a typical equilibrium diagram. Equilibrium diagram is nothing but the phase diagram of a eutectic system, that is a eutectic phase diagram, and you have to explain what is limited solid solubility as well. So you must, if you are drawing a latent diagram, you must know what is alpha phase and what is its limit of solid solubility, that is 19% of tin in lead, and what is beta phase and its limit of solid solubility, that is nearly 2% of lead in tin. And you must explain the various features in this phase diagram. Okay. So the rubric for this question may be like this. The total question, as you can see, it is for 16 marks. But the distribution of scores may be like this: 6 plus 6, 12, plus 4, 16. So 2 marks may be awarded for stating what is eutectic reaction with the necessary diagram that was seen in first slide. 6 marks may be allotted for drawing the phase diagram legibly and marking the different regions and boundaries in a clear way. And of course, if you are drawing and marking it clearly, you must be able to put it in crisp words that are clear and legible. Must be able to explain the phase diagram in detail. This may carry a substantial fraction of the marks, that is 6 marks out of 16. And of course, the concept of limited solid solubility with reference to the eutectic system, which can be explained from the phase diagram as well. If this was explained clearly, you may gain another 6 marks. And finally, what is an eutectic alloy? Because you are asked about the eutectic phase diagram in detail. So, you must explain what an eutectic alloy, its characteristics. When I say its characteristics, it means the composition, the temperature, the eutectic reaction that occurs along the eutectic horizontal, and what will be the microconstituents at the end of the eutectic reaction. If you explain all these in detail with legible, clear, neat diagrams and explanations, you must be able to get the full 16 mark out of the allotted 16 marks. So this is for the first question, which runs as draw a typical equilibrium diagram for a eutectic type of system with limited solid solubility and explain its important features. So for that question, the rubric or the blueprint given to the examiner would look like this, and the student must understand the relevance of his answer based on such a rubric. So during assignment, I am providing you with such a rubric, and so your assignment answers should be based on this rubric. The next question that is oft repeated in the examinations is explain in detail the different phases in eutectic phase diagram. A more direct question, because in the previous question it was given as equilibrium diagram, which is nothing but the phase diagram. Here they are asking you to explain in detail about the different regions in the phase diagram, and another major portion is the microstructural changes during cooling. So the rubric for this question would be 4 marks for drawing and explaining the eutectic phase diagram in a legible way, and then explaining what is an eutectic alloy and its characteristics along with microstructure evolution, showing the microconstituents. That is, for a eutectic alloy, it is just a eutectic mixture, that is a lamella of alternate alpha and beta phases. Then explaining what is a hypoeutectic alloy, that is an alloy with 19 to 61.9% tin is called a hypoeutectic alloy, and on cooling below the eutectic horizontal, it forms microconstituents containing pro-eutectic alpha and eutectic mixture or eutectic microconstituents. So you must explain the microconstituents of hypoeutectic alloy as well, and you have to explain what is hypereutectic alloy, that is an alloy containing 61.9% tin to say 97.8% tin, and the microconstituents in this case would be pro-eutectic beta and eutectic mixture. So I hope this rubric would help you understand how to answer in relevance and concurrence with the question, so that you can score at the maximum. That's why I am giving you this rubric for answering your assignments. Make sure your answers are consistent with the requirements in the rubric. I hope the eutectic system has been discussed in detail, and on reading through the given material, I wish all of you would score the maximum provided this question comes in your exam. All the best.